Welcome to the second part of lecture 19 on graph theory. So, today we will talk about planar graph. A graph is planar if it can be drawn on plane such that the edges meet only at the vertices. And at the end of this lecture, we talk about how to characterize planar graph and coloring of planar graph. Okay, let me start with the formal definition of planar graph. Definition: plane graph is a graph that can be drawn on the plane so that its edges meet only at vertices. Okay, so let me give an example of a planar graph. So, this is a planar graph, though you can see that the two edges cross here, but we can redraw it. So, K4 so that the edges meet only at vertices. Well, K4 is a planar graph and three plane drawing of K4 are so we need to draw the edges in such a way that the edges meet only at vertices. So, this edge, instead of drawing in this way, I can redraw it in this way. So, now you can see that the edges, all the edges meet only at vertices, and another drawing of the same graph K3 without any edge crossing. So, this is an edge crossing. So, this is not allowed in planar graph. So, K4 can be also drawn in this way. So, this is also K4, and you can see that there is no edge crossing, the edges meet only at vertices. And the other drawing is this one, 4 vertices well. So, this has now degree 3. So, every vertex has degree 3. So, this has degree 3, this has degree 3, this has degree 2 and this has degree 2. So, I will join them by an edge. So, this is another drawing of planar drawing of K4. So, K4 is a planar graph. So, two graphs which are non-planar are shown below. So, one is complete graph with 5 vertices. So, this is a complete graph with 5 vertices k 5, and you can try to draw this graph on plane without edge crossing. It does not matter how hard you try, you can't draw. So, we will also try to do that, but you will not be able to do that. So, that is why k 5 is non-planar, and also we will prove formally that k 5 is non-planar graph. And other non-planar graph is, this is also a non-planar graph, complete bipartite graph k 3 3. Okay, so this is also non-planar. Well, as I said that let us just convince ourselves that we can't draw this graph without edge crossing. Okay. So, I am trying to draw all the edges without edge crossing. Now, I can draw these 2 edges, no problem. Still now there is no edge crossing. Now, this vertex is adjacent to this vertex. So, I can draw this way to avoid edge crossing, and this vertex is adjacent to this edge, sorry, this vertex is adjacent to this vertex. Right. Now, what we are left is that this vertex is also adjacent to this vertex, right. So, that one we can't draw without any edge crossing. So, one way to draw this edge is directly you just draw this way, but this is the edge crossing here. The other way you can draw is this way, but here also you have to cross this edge. So, you can try and convince yourself that it does not matter how hard you try, there will be edge crossing. Okay. Now, we talk about 2 operations. One is deletion of an edge UV. Okay, so we suppose this is the edge UV, and this vertex is adjacent to some other vertices also, and similarly U is also adjacent to some vertices, and the deletion of this edge UV will result in this graph. You will be left with this graph. Okay. The other one is important, which is called contraction. of an edge u v. So, contraction of this edge u v results in this graph. So, what it does is that this contraction operation, it removes the edge u v and merge two vertices u and v into one vertex. So, contraction u v removes or delete the edge u v and merge the two vertices u and v. That is what the contraction operation. So, we learned about two operations, one is deletion of an edge and contraction of an edge, and these two operations will be used frequently in planar graph to prove some results on characterizing planar graph and some other related result in this area. So, next we learn what is a face of a planar graph. So, we will start with this definition. Let G be a planar graph and consider the region bounded by the edges of G. These are called faces. Okay, let me explain this one. I draw K4. It's a complete graph with 4 vertices. And so, as I said that consider the regions bounded by the edges of G. So, this is one region which is bounded by these 3 edges. So, this is one face, let me call this as face 1, this is another face, face 2, face 3, and this region is also called a face, this is the face 4. Okay. So, this is what the definition of face, and this F denote the number of faces. So, K4 has 4 faces basically. Okay. So, next we prove a very famous result due to Euler, which relates the number of faces, number of edges and number of vertices of a planar graph. So, here is the theorem. And this is due to Euler. if connected plane graph G has exactly V vertices, E edges and F faces, then B minus E plus F is equal to 2. Okay, so let us understand that what you mean by this one. So, I will draw the K4 again, and we know that this graph has 4 vertices and 6 edges, E equal to 6, and it has 4 faces, F equal to 4. So, you can see that V minus E plus F is equal to 4 minus 6 plus 4, which is equal to 2. And this is true for every connected planar graph G. We are going to prove this one, and to prove this we use the induction technique. We use induction on V. It is a beautiful proof. So, basic step is, so induction on the number of vertices. So, we will prove that this result is true for all graph, all planar graph with one vertex. Okay. So, only one vertex, that means this graph could be simply this one. If E equal to 0, then the number of faces of this graph F is equal to 1, and you can put the you can check the formula is correct, because V equal to 1, F equal to 1, E equal to 0. So, this is equal to 2 and the formula holds, right. If E equal to 1, that means it has one edge, that edge, one edge, one vertex. So, that edge has to be a loop. Now, we can see that this graph has 2 faces, then F is equal to 2. So, E is equal to 1, V equal to 1 and F equal to 2. So, the formula holds. If E equal to 2 edges, that can be like this. Now, you can see that this graph has 3 faces, one face here, one face here and one face here. Then F is equal to 3 and the formula holds. And similarly, you can check, you just keep on adding the edges. Once you add one edge, the number of faces also increases by 1. So, the formula will be true always. So, each added loop passes through a face, right. Once you add a new edge, it passes through a face and cuts it into two faces. Right. So, once you increase E by 1, the face number of face also will increase by 1 and the formula will be true always. So, what we have proved is that this Euler formula is true in the base case when the number of vertices is equal to 1. Next, we prove in general that the induction step here V greater than 1. Okay, so, the idea is that if it is true for a graph with V minus 1 vertices, then it will be true for a graph with V vertices also. Since G is connected, we can find an edge that is not a loop. See, the number of vertices is strictly greater than 1. So, suppose at least 2 vertices are there in the graph, and then all the edges can't be just loop because the graph is connected. So, there has to be an edge which is connecting two vertices, two distinct vertices. So, we can find an edge that is not a loop, and then when we construct such an edge, we obtain a plane graph. G prime. Okay, let me just give another example of contraction I wanted to give before. So, suppose this is an edge u v, okay, and I want to contract the edge u v. The contraction of edge u v will result in this graph. So, what it does is that it delete this edge, delete the edge u v and merge these two vertices u v into one vertex. So, the result of this contraction will be this. So, you can see that these two edges now become the parallel edges here, right. So, this is also a result of contraction, and we obtain a plane graph G prime with V prime vertices E prime edges and F prime faces. So, what we are doing is that we are just constructing an edge of a planar graph, and then in the after construction we get the graph G prime, which has V prime vertices, E prime edges and F prime faces. Then one thing to observe, that the construction operation does not change the number of faces, but it reduces the number of vertices and edges. We will try to let me just add one more edge here. So, the contraction will result in this graph. So, at this moment I can see that this graph has 3 faces. This is one face, this is another face and this is the other face. So, this graph has number of faces of this graph is 3. Let me call this graph as G and this is G prime. After constructing the edge u v, I get another graph, and this graph also has 3 faces. So, that is what it says, the contraction operation does not change the number of faces, but it reduces the number of vertices and edges. So, the number of vertices of this graph, the graph G, was 1, 2, 3, 4, 5, 6, and this graph has number of vertices 5. This graph has number of edges 3, 6, 7, and this graph has number of edges 6. So, it is very clear that the contraction operation does not change the number of faces, but it reduces the number of vertices and edges, right. Number of faces and edges by 1. So, in general V prime is equal to V minus 1, E prime is the number of edges in the graph G prime is equal to E minus 1, and F prime is equal to F. I want to know what is the value of this one, V minus E plus F, and I can write this thing in terms of V prime, E prime and F prime, which is V equal to V prime plus 1, E equal to E prime plus 1 plus F prime. So, which is equal to V prime minus E prime plus F prime. Now, see this graph G prime has one less vertex. The graph G prime has V minus 1 vertices, and by induction hypothesis the Euler formula is true for G prime. right, because it has v minus 1 vertices, and we are trying to prove that the Euler formula is true for a graph with v vertices. So, since the Euler formula is true for a graph with v minus 1 vertices and v prime is exactly v minus 1. So, this is the Euler formula is true for g prime. So, I can write that this is equal to 2, and I have proved that this is also true for g. Okay. So, this is how we proved the Euler formula for planar graph using the induction technique. Thank you very much.